Identify with reason. Which of the following are eigen functions? So it means you have functions there. Which of those are eigen functions of the operator ddx? Now, I want to start it this way. Do some bit of a revision. I've talked about the Schrödinger equation, and that it's written. Oh, okay. It's written in the back. It's written like this. This is general expression of the Schrödinger equation.
Why are there so many versions?
This is the general one.
Yes. Why there's another one, there's another one. There's so many of them.
Now,
so many.
This is the summary. This is the summary. This form. Yeah. We're going to what you're saying there's many of them. This is the summary. We are interested in the time independence. Now, what we have here is the Hamiltonian. This form here is called the Hamiltonian form of the Schrödinger equation. Hamiltonian because this operator here, you have got the operator here, and you have got the wave function here. These two are the same, remember? And you have what we call the eigenvalue here. Eigenvalue. All this is in your textbook. So I thought I would just do some revision here. So, what this equation is saying is that if you have a system, let's say a particle, and you know now this particle has got this wavelength, let's say and have more than one wave, wave function, wave function. Or maybe let's talk about wave functions. Quantum mechanics says that each and every particle that exists has got at least one wave function. That describes all its properties, everything about that particle, everything, all properties it has, they are packed in that wave function. So this equation, the Schrödinger equation, takes that wave function and applies to it an operator. Now it depends what observable we want. What property do you want to say to calculate? Is it energy? If it is energy, you use this one. You use the Hamiltonian. Okay? You subject that wave function to the Hamiltonian, and the Hamiltonian will give you an eigenvalue and return your wave function as it is. Now, let us suppose now we're looking at a particle, a free particle. Or let me say now, first, what is this Hamiltonian? Hamiltonian is an expression, it's an operator. How does it? It's a mathematical expression, or let me say, you write this thing as, again, we're looking at a particle that is moving along a string. Okay? Along a string. And so we write a Hamiltonian. Is that correct? Is it correct?
Yeah, it's
correct.
It's correct.
So, this is the operator. So it means, once you have your wave function, you must subject it to this operator. So that simply means that you multiply it by this with. Physicists don't really say multiply. They say you let the operator operate on the wave function. So it operates on the wave function. See? So, and they say it's not like multiplication. Multiplication is something else.
Operation.
Yeah. So it's an operation. So it's an operator. So it operates on that on your wave function and gives you energy. So if you have that's the Hamiltonian. It's called the name Hamiltonian. So if you have a Hamiltonian, immediately you know you expect energy out of it. Okay? So you might have a linear momentum, for instance. So once you have linear momentum, you expect an eigenvalue for linear momentum there instead of energy. Okay? So, now if we say we are looking at a free particle, what do you mean by free particle? We mean one that is experiencing no external interference. A free particle, that's one that is one that is not like us. We are under the influence of gravity here, so we are not free. So one that is free is in space. A particle is free. There is no field around it. The Earth is under the influence of the sun, so it's not free. It's not a free particle. So for a free particle, this term here is 0. So we remove it. So we remove it. Now, once we have removed this, what we can rewrite this equation here as equal to minus okay. So you see that we've rewritten that equation. So now the equation says to us that that operator leads us to this eigenvalue. This is the eigenvalue and returns our wave function. So it means, so we call this function an eigen function. Call it an eigen function. In other words, every function that behaves like this, when subjected to an operator, it gives you an eigenvalue in itself. That wave function is called an eigen function. It's called an eigen function. So the next question is this, that, or the next issue we want to address concerning now a free particle is that, or the wave function is that we never know, we never know what the wave function of a particle is. We must always look for it. Must always look for it. So the practice is the following: that if you start let's say, for instance, you start with this function here. And you say this is your general equation. And you work your way through, you test everything about this equation. You end up realizing that this part here does not work. Just doesn't work. In fact, you realize that only the part on the right is an eigen function of this. Okay? So, and therefore, you rewrite your, oh my goodness, you rewrite your equation so what I'm going to do, I'll remove the B, because the B simply is the it's a constant. Yes. It's better to put it there. It's just a constant. So let us remove it and then work with this. So now, if we subject this wave function now to the same operator, what do we get? We get, or let me say, let me write a dash. By dash, so let me say 2 dash. This, okay. So what do we get? Minus K it looks like you have you looked at it? Have you looked at this? You've written the assignment. So what do we write there? Okay, this is what you get. Okay, so what is this saying? This is saying that is your eigenvalue, which is the same as that. Because we're subjected both to the same operator. And they give us these two eigenvalues, meaning that minus k squared is equal to minus 2me divided by that. That's what it means. Any questions? So, this is the path you take as you go into the solution for a free particle. Because this will end up, if you remove that, you can write here the square root of 2 to the power half, as you please. Same thing. Now, the reason why I'm doing all this is to come back to the question. But the question says that you must find out if those functions here are eigen functions of the operator. So, let's start with the first one. Where's my red? So can I remove this? Thank you. So, what we are saying is that, well, the question is, e to the power minus I k x. That's the function we have, isn't it? So, there's a plus here. Let's move plus. So what do we expect? If this is an eigenvalue equation, we expect to get an eigenvalue here times that's what we expect. If it is an eigenvalue equation. So what do we get here? Ik, isn't it? Yes, Ik. Which means that the function is an eigenfunction, because we are able to take the first derivative and get the original wave function times a constant. Okay? By constant we mean we get something that is independent of x. It doesn't change with x. If you get something that changes with x, that is not an eigenvalue. So, I think the next one is K. Now, one.
It's a zero.
It's zero. Zero. If it was, what should we have to get a 1?
8.
So this is 0. Get a 0. So that is not an eigen function. And I think you must have been able to solve all those, isn't it? So I think, and the textbook, I think the textbook also explains this at large. So we shouldn't waste a lot of time. So we can go back to question 5. The point is made. And you see very soon which point that is. You see soon which point that is. The question 5 requires that we should normalize the wave function. We're given the wave function, but I also think you've gone through this. There's a good example actually in the book. That is just not different from this. Yes?
Question. So, in the exam, will you give us the formula?
Which formula?
The integration formula.
Like a formulation?
Like this one requires a formula.
Yes,
No, not the two.
Go back to the thing at the back of the textbook.
In the exam, I will give you equations in the resource section.
Okay.
That's a sheet or something.
Yes. Yes. In fact, there is everything there. The data you need, the equations you need, and what else? The
values of
periodic table of elements.
yeah.
The contents.
The contents will be there, so you don't have to memorize anything.
Right.
Even though,
You can't say when you need to be able to write.
well, this has nothing to do with what you're supposed to. Or supposed to. Even though some of the stuff goes naturally into your blood with time. It happens naturally.
My blood is thick.
Your blood escapes chemistry. No blood escapes chemistry. So, but you'll have all the equations there. So, what I want to say here is that first, you must know that there is something called normalization condition. And writing a normalization condition should be part of what goes into your blood.
Right.
So let's talk about this. This is called the zeroth moment. The zeroth moment, or the normalization condition. Zeroth moment of probability. It simply says that it assures you that within that space, tau stands for space. That is, you integrate from minus infinity to plus infinity over all the space you have. And when you are done with that integration, you must have a value of 1. for a particle. In other words, you don't have to integrate from infinity to infinity if your particle is in a box from A to 0. You integrate within that space. Okay? So, if you're talking about Cartesian coordinate system, for instance, so that will be your dx, dy, dz. That is your space. Tau is in the Cartesian space, dx, dy, dz. That is if you are working on a 3-dimension. But if you are working on a single dimension, particularly on a string, on a single dimension, you take one dimension, so you'll have a dx there. Okay? But the particle must be in that space. It means that integral must be equal to 1. So, now, that is why, so we always work with normalized functions. So you cannot take a wave function and just do anything you like with it. First thing that you must make sure is that it is normalized. So, my question, is that wave function we have normalized?
At the top?
Yes, the one at the top.
No.
It doesn't look normalized. Do you want to say something different?
Next question you asked was to normalize the equation, the equation. Isn't it, when you say normalize, isn't that you're checking that it's normal? To see that it equals to 1?
Normalization, no, first, the wave function describes the particle. Describes the particle, okay? So, outside the space we're talking about, this wave function is 0. So it's only positive within the space we're talking about. So, integrating on this, on the particle outside will give you 0, because it seems there is no probability of finding it outside this space. Okay? So, normalization simply makes sure that the wave function you're working with gives you says the particle is certainly within this space.
Thank you. Oh, so normalization gives you
there is no probability of finding it outside.
Okay, understand.
Okay?
Limitations.
Yeah.
Limits you to that space.
There is no possibility that the particle, mathematically, it's just a question of mathematics. You are saying that the particle is within this space, full stop. Okay? So in order to normalize an equation, we multiply by n for normalization. We multiply by a constant. There is a constant. We are saying that the normalized version of the wave function is times a constant. That's the constant we're looking for. How is it supposed to look like? Okay? How is it supposed to look like? So, tragic. This is a hazard. This is a hazard. So, what do? We go there. And multiply by n. Okay?
It's not normalized.
It's not yet normalized. But we want to normalize. So we change this. Change this. Let's say to N and to right. Okay. So this simplifies into this. Okay? So we can simply take that there and put it here. Now, we shouldn't worry about the star. The star is written normally to accommodate complex numbers. You know what complex numbers are. So, if we've got a complex function, we put it there. Put the complex form here, and we put what do you call it? It's real part there. Okay. So now what will happen? What will happen now is that we rewrite this. This is going to be a so N, and we have sine squared 2 pi dx. So, if I should ask you in the exam to do this, this will be given. This integral will be given. Solution to the integral will be given. So you shouldn't worry that the solution is not there. So what you will get, so you will simply have to take that solution. Don't forget the following. So you come and write the solution here. Equal to 1. Write your solution there. So in our case, it is, what do we have? So the solution you get in the resource section is 1 over sine 2AX. That is the solution. I mean, of the integral. So this is what you get. So this is what comes in here. Now the question is, you look at your equation. Your original function here has got this. And you have got 2AX. So everything, your X is the same, and everything else. So you've got your 2 pi over L is here. Okay? So your A is your 2 pi over L. Because if this function is just pi, if it is just pi x over L, the solution you have here is 2ax. What you have is 2ax, okay? Which simply means that your A is pi over L. Okay, I mean it's your A is pi over L, yes. So your A is the constant. Everything that is A is everything that is not X here. So if you go 2 pi over L, put it under A, and you end up with in our case, you end up with a 4 pi over L, isn't it? Okay. And your A here is 2 pi over L, so it means it will be an 8 pi, and your L goes up there. Okay? So, now, so once you have, you will see that your normalization, once you've solved this, you must remember that you have got to take your solution between these limits. You insert your L first, and you subtract, and then you insert your 0. Subtract one from the other. You will end up with your N being equal to, what's the constant? 2L of 2 over L to the power half, or root, or square root. So that is your normalization factor now. So it means you take now this here and you write it there. And then you have your normalized function. You have your normalized function. This is also done in the textbook. I'm just doing it because the equation we're working with here has got 2 pi x over L. But in the textbook, we have pi x over L. Okay? So, yes.
There's no integral for cos. There's no integral for cos square, right? With cosec. I can't remember, but one of them, when I was looking at the formula, the integral formulas, I think it's cos. There's no integral for cos square, so you would never give us that one, right? I'm just checking. I haven't seen it on the formula.
I won't give you some things that are out of the ordinary. I won't give you things that are out of the ordinary. In other words, I won't waste my energy on tricking you, because I still have to mark all that stuff.
Just remember, you're being recorded.
Well, I don't care about being recorded. I don't care about being recorded. Everything that I'm teaching is within syllabus.
All right.
Within syllabus. In fact, I have asked students in the past that they should go and when they ask me for a scope, I've told them there is no scope. If they want to complain about me not giving them a scope, they must go to the dean and tell him that. I don't give scope. I don't give scope. What I'm saying to you is that if you master everything that is in all these three assignments that you have, I'm not saying that you should memorize what is in here. I'm saying you should master it. You should understand it. Then you are certain of a distinction in the exam. So there's no trick in this. There's nothing hidden. It's just. And you've got all the help as you write your assignment. Even though I keep on surprising myself. Why no one calls? Why no one writes an email? And I simply assume students know what they are doing. If I tell them to consult me when they are writing their assignment, and they don't, and then I still get something that is somebody writes 2 lines and submits. That has got nothing to do with me. That has got nothing to do with me. In fact, next time the dean asks to see me on whatever matter, even if it has got nothing to do with assignments, I'll take those assignments and go and show it. Even if it has got nothing to do with assignments or teaching, I'll take those assignments and go and show him it. Look. Because as far as I'm concerned, I'm dealing with adults. If I tell them that is the way to success, and they decide to go into the bush, how can I stop you? So, the next section, 5b, says calculate the probability of finding the particle between the following boundaries of a 7 nanometer long nanotube. So that is what we're going to do now, because we have normalized the wave function. If we hadn't normalized the wave function, we wouldn't be able to calculate the probability. Okay? So, calculating the probability. Now, your textbook says, says calculating the probability is given by this function here. Now, the question is, what does that mean? What does that mean? So, in our case, we know this function. We've normalized it. So that's not a problem now. We are given that we want to find the probability in the first instance. In fact, I just want to do one because the other one is the same thing, so I will be repeating myself. So we want to be looking at the probability of finding the particle, only one-dimensional particle from within this range. And what else can we write today? What else can we write? All right, because we have the solution, let us simply write the solution, isn't it? So our P will be why do we have why is this now without the square root? Because we've squared. Good. So this is now you do realize that everything, there are no units there. We know that L is equal to 7 nanometer. So if there are no units there, it means X is given by what has units. So the units will cancel out. So you simply put those values themselves there. Okay. So, and I did the work and got 0.0 This is what I got. Question is, why when you've done it, when you've done this work, you ask yourself, why do I get such a value? Isn't it? Everything that you, how much do you expect over 7 nanometer? What value do you expect? If you integrate, if you look at the probability between 0 and L, which is 7, what do we expect? 1. We expect 1. What range do we have here?
5.95 to 5.05.
We have got, going from there to there.
Yeah.
How much do we have? We've got 0 point?
4.95.
The
first one, oh yeah. Oh yeah.
So how much do we have? 0 point?
0.1.
0.1.
1.5. 0.1 or 0. Yeah, 0.1.
Remember calculating it.
Look, it's 0.5 and 0.5, 0.1.
49.
0.1.
Calculate. Y'all don't believe me. 0.1.
Fine. If you say it's 0.1. So.
Yeah, 0.1.
But look at the.
Just wanted to make sure.
But look at the probability of 10%. That's 10%, isn't it? It's supposed to be 1. If now the only reason is that, I mean, no, not 10%. It's 2.7%. 2.7 the probability. 2.7%. But it is understandable because we are looking just at 0.10 nanometers when we have got a length of 7 nanometers. So the probability we're looking at is very small. It's very small. So what you can do is, I hope you have the interest and the curiosity, is to increase this range here. Increase this range here. Keep on increasing it until you get to 7, and see how you should get to 1 at some stage. Once you get to 7, you should be able to get the value of 1.
When you add all those probabilities up.
Well, of course, they must all add up to 1. They must all add up to 1. They must all add up to 1. Okay? So you can do the same with Roman figure 2, where the difference again is
I want to give an answer. Someone's going to stick with a calculator.
So you can do Roman figure 2.
0.1.
Yeah, it's also 0.1. You see? So you can
calculating that.
You can calculate all those probabilities. Like I'm saying, they must add up to 1. From 0 to 7, they must add up to 1. So, question 6. Now,
Yes, let's do question 6E.
Question 6E, yes. Now, question 6E has got to do with the fact that we must work with a normalized wave function. Normalized wave function. We left it for last because there's the stuff above that we had to know first. Now, we need to calculate the expectation values of x and x squared for a particle in the state n equals to 2 in a square well potential. What is a square well? What is a square well? When you said when you were writing this assignment, you did not ask me what a square well is. So it means you know what a square well is. So I'm asking, what is a square well? It is in your textbook. By the way. Is there any question on this? Probability. Go and work it out. Go and work it out. And ask me if you've got a problem. Go and calculate these probabilities. And ask me if you've got a problem. You can put it on discussion forum if you want to remain anonymous. But I don't think the discussion forum allows that. There's no anonymity there. But still, it doesn't stop you from asking. So, what is a square well? What is a square well?
The text doesn't really explain. But another text,
it's very
it's like this.
What is a square well? At honors, you should be able to ask questions.
The particle in a box is considered a box, right? Like it's here to there. Then a square well, it also includes walls that go up, right?
No.
I read the wrong book then.
No. I said to you that when we're saying it's a one-dimensional box, we're looking at something that looks like a string. Like a string. If we're looking at a two-dimensional box, what are we looking at?
X and Y.
We're looking at a plate. It's only a plate that has got two directions like a string. There's one side, X, there's another one. But it's just a plate. It's just a plate. When you have got a three-dimensional box, three-dimensional, then you have got a volume.
See, that's what I was saying about the...
But it's a three-dimensional one. That's a three-dimensional one you're talking about. The two-dimensional is plate-like. It's all in the textbook. I must begin to wonder how you read that textbook. Maybe I should add this. There is no sentence in that textbook that is just there for the fun of it. Every sentence there has got a purpose. Every sentence has a purpose. You must ask yourself, why has this been written here? What am I supposed to learn out of it? That is how much attention you pay when you're reading that book. So, there's even a diagram of a plate in the textbook. There's even a diagram of a plate in the textbook for a two-dimensional box. So, only when these two sides are equal. So you've got L, X, and L, Y. The wave function, let me see. The wave function is let me see. Now you are saying to me I should have brought my own book. So, but anyway, the two-dimensional box has got lengths Lx and Ly. When Lx is not equal to Ly, you have a rectangular box. When they are equal, you've got a square well or square box. When they are not equal. When they are equal. And the wave function, so in fact, when you go to the two-dimensional picture, you learn about separation of variables. Did you see that in the book? Separation of variables. When you solve the Schrödinger equation, did you meet that? Did you see it anywhere?
Yeah, something like that.
Oh, you have a textbook here. So the problem you don't know where to find it.
It's English.
Oh, it's English, I see.
It's very hard.
What were you expecting?
Chapter 7.
What were you expecting? But you know which chapter it is, so what is the problem of finding it? If you know which chapter it is. So, you've got the single dimension here, you've got there. So, look. What's that? That's a plate. That is a plate. So, the wave function you have, in fact, because there is a separation of variables, you can write two of those wave functions. One for the x direction and another for the y direction. But for the total wave function, you write a product. There. There is the product. Once L1 and L2 are equal, you have got a square well. You have a square well. So it's not that the function is not there. It's in the book. It's in your textbook. And I'm saying that use the one for n equals to 2. So it's not a struggle. Everything is in the textbook. All I can say is that if you neglect your book like this, you are taking a huge risk, serious risk. Sometimes I ask myself, if adults work hard for their money, and they come and register with their money they work so hard for, and have got no purpose of passing, what sense does it make? It doesn't make sense to me. If you work hard for your money and you go and register at a university, you've got only one purpose there, is to pass. There's only one purpose there. So, risking hard-earned money and not passing, it's a conundrum to me. It's just something I cannot explain to myself. Because it's not that the answers are not there. You have the answers in front of you. You have your textbook, you have your assignment questions. So, you don't have, I mean, even the recommended text that I'm talking about, even the recommended text that I'm talking about is an additional help. Additional help that you must pass this module. Now, I hope that I haven't started looking at the assignments. I just browsed through and saw something hazardous there. I saw something hazardous there. Now, I'm not a preacher. I don't preach in my spare time. I'm only a teacher. So the only thing I can say to you is that there is only sense in science to deal with facts in front of you. So that textbook you have has got answers to everything that is here. And the little that is not here is in the recommended text. And the recommended text is in the library. I cannot exonerate you from consulting the library, because that is what you are supposed to learn at honors. At honors, you are supposed to learn this introductory year into research. When you are done here, you'll be reading on your own. We'll be expecting you to present in the department. You have to go and get the literature on your own. We won't be accompanying you. You won't expect anybody to hold hands with you and take you to the library. You've got to go on your own. So this is the introduction. Start reading willingly beyond the textbook. Beyond the textbook. I said this in the last VC. I'm saying it again. So, if your performance is to improve in the second assignment, you need to start reading. You should start reading. So, expectation values. What are expectation values? When you do an experiment, you know that when we measure any observable, because anything you measure is an observable. Anything you measure in the laboratory is an observable. What we do is we measure, we do several measurements, many. Out of those measurements, we are looking for the average value, because you need to report those results. One, we are looking for the standard deviation. We are looking for the variance. You need to know how your results are behaving. I mean, if you've got some measurement, so and they have such a distribution about some mean value. That mean value is what we calculate as the expectation value. Okay? After we've taken these many measurements, we build a mean value. So quantum mechanics says you write your mean value like this. your wave function is already normalized. You cannot write this if it is not normalized. Your wave function is already normalized. So that mean value is the same as we get in experiment. But, so, even if the other value we can calculate is the second moment. We said this is the first moment, this is the second moment. Probability we said was the 0th moment. So, the second moment we call variance. It's not written differently. So, this is easy. This is easy stuff. Because these integrals exist in tables. They exist in tables. All you have is you take this normalized wave function, you multiply it so it's a square. You might have this in front, so you have got x squared times sine squared of pi x over L, something like this, dx, an integral there. This whole thing there is an integral that you can find in the list. You can find it listed in CRC. Do you know what CRC is? Good Lord. There's a list in the library that is issued every year. It's a book, actually, of constants and equations and so on. It's called a handbook. It's a handbook of chemistry and physics, of physics and chemistry. In short, CRC. All that is written on the front page. When you get into the library, in the section where you find chemistry and physics, that's where you'll find that thick handbook. And those integrals are in there. They're in there, but I will list them also in the exam. So yours is to exercise, learn to exercise with them now, and ask. What I will do is, of course, I will issue the keys, but you need to realize that you cannot memorize keys because I can change anything there. I can change a small thing and then you don't understand what's going on. You better understand what's going on. That is understanding that is learning. If you memorize stuff and you get into the exam, something has changed. Something that you would have learned to observe if you had engaged yourself. I mean, then you have a problem. So, integrals like this are listed. And should you need them in exam, they will be in the resource section. So there is nothing you need to memorize. In fact, what I'm saying to you is that for this task here, question 6E, this is simple. Everything was you. In fact, the hardest that you could have done is to go and look for these integrals and find them and put them there. That is the hardest you could have done. You could have experienced. Go to the library and find this list, and then include it in your assignment where you got them. Where you got them. Any information that is in your assignment and is not yours, not written by you, it comes from somewhere else, must be acknowledged, else it's plagiarism. Now, second, internet is not a library. You cannot simply go and copy things from the internet website and say, I got it from this website. There are many students all over the world. Some who think they are professors and they write things and post them on the internet. And you come and copy that and you say, this is my reference. Reference is going to the library. That is where official academic literature is. Official academic literature that you can reference is in the library. That is the stuff that you can stand up to with pride academically, not something from the internet. So as far as I'm concerned, I don't accept anything that is from the internet. It's flawed. There are many flaws there for people writing things they don't understand and putting them there. The library is your boss. The one that has what you want. So, any other question? Oh, let me say, now, matrices, instead of the variance, something that is very interesting that we use often is the standard deviation. The standard deviation has this form here. We've got the value that is measured anywhere along this line. Measured anywhere along this line, minus the mean value. And then, because this thing here, this difference can be negative, we square it. Now you can see that this value is taken at each and every value. And we take the mean of this. So, this thing here is the square of the standard deviation. The spread of your values. So you realize that if you've got such a curve like I've written here, and this is larger or equal to 0. Larger or equal to 0 because you've got a square there, so everything is positive. Now, large, very large, larger than 0 is what you have here. But could have been better. You've got a spike. You've got just a spike that lies around the mean value. That is what every scientist wishes to have.
Percussion. It's called percussion.
Gaussian. Well, they both have the Gaussian form. The thing is, you want to have a very small value of the square of the standard deviation. Here. Or here. You want to have a value that is close to 0, very small. If that value is large, it means your values are everywhere. They are scattered, large scattering. It means there's a lot of error. There's a lot of error. Okay?
It's not consistent.
You see? There's a lot of error. So we want, this does not yet mean that your value is accurate. The spike simply says that you are precise in the measurement. Your measurement might be precise around an inaccurate value. Because an accurate value is the one that is close to the real value. Okay? One that is close to the real value. That's an accurate value. One that is precise is one that is thickly situated around a mean value, your mean value. So, if your mean value and that of the and the real value are the same, and you've got such precision, like a spike, then you've got good experimental results. That's what you want to have. So this is what that question is about. It's about calculating these. The first and the second moments. First and the second moments. In fact, I realize that next time I will ask for the standard deviation, the square of the standard deviation, because it's closer to, in meaning, to experimental measurements. So, any questions? So, question 7. Again, there is an example 71 in your prescribed text. So, if I say 71, it might be 7E1 in the. We are using the 11th edition, so the 10th edition might be 7E1. But the 11th edition is 7D1. That is where you look at where this question comes from. Now, in the exam, I didn't write the structure here because I expected you to find it. Vitamin A. It's a conjugated compound, hydrocarbon, with 11 double bonds, conjugate, 11 double bonds. So, which means the transition we're talking about is from N11 to N12. That's where the homolumo lies. That's why the homoluminize. But because it's a straight chain, the approximation is that of a particle in a box. Remember, I talked about a string. So that approximation works. In fact, there are examples of experimental measurements that are in very good agreement with this approximation. This is why it is important. And the conjugate cyclic hydrocarbons are approximated using the particle on a ring. That is rotational motion. So these two are the subject of a material in this module, even though I did not include the cyclic one. But once you do the linear conjugate molecules, you understand what is happening when you do the cyclic. In the textbook, the cyclic is there as well. So even though they are in different sections, but when you look under rotational motion, the example for cyclic hydrocarbons is there. I don't think we need to delve much into this because it's obvious as far as I'm concerned, except if you've got other questions. But there is if you want to understand more about this, you need to, I think you must have gone through this because it's in the first assignment. You know what I'm talking about. I shouldn't even have mentioned that there's an example 71 because you already know. So the questions here are just that you need to find the energy separation between ground state and the first excited state. And B, you need to find the frequency of radiation. Radiation that is emitted upon transition between the two states. So this is a rather simple exercise. Now, question 8. Question 8 has got to do with the variational principle. Now, this is also in your textbook. The idea behind the variation principle is simple. Is that, you remember we said, when you want to solve the Schrödinger equation, you need to find the wave function. You need to find the wave function first. And then, even the Hamiltonian, or let me say operators in general, or the Hamiltonian for a particular energy system, you need to construct it. It's one of the tricks of research, that building those Hamiltonians is a thing of wonder. And also approximating the wave functions of molecules, different molecules. It's work. So there's work involved. So when you find values that correspond with spectroscopical results, because spectroscopy gives what molecules in practice have to show, except for maybe small deviations which can be explained also. Remember I said chemistry is a mathematical construct actually. So there is nothing that you cannot explain in chemistry that is divorced from mathematics, basically. And what molecules do can always be explained. You just need to understand what they are doing. So, spectroscopy is a means of probing molecules and finding answers. And then on the other hand, we've got the theory that we are dealing with here. So what we intend to see is that this theory speaks the same language with the experiment. So it's always a problem when experiment says one thing and a theory says another. See, it's always a struggle. So, but that is the. So in this case, the variation principle says that when you guess a wave function, that wave function, the energy you get for that wave function cannot be less than the actual energy. So it means if experiment gives you a value sits here, energy, you cannot find a value that is less than that. Because we take it, experiment gives you the real thing. So this, so what you try to do in formulating your wave function, you want to get as close to the value as possible. If you find something lower than the real thing, you know you're wrong. You know you're just off. So that is the summary. That summarizes what the variation principle is saying. For 6 marks, actually, is I think it's a bargain, because it's all in the textbook. All you need to do is to look at what the various texts are saying, and then formulating your story. So, and then you get those 6 marks. So, I think, geez, oh, one hour. All right, but you've been patient. I'm impressed by your patience. I hope. But the question 9, like I said, question 9 and 10. Let us meet in the discussion forum. That is where I will upload. We meet in the discussion forum. I'll send you an SMS first. Okay. I'll send you an SMS when that begins. But even without that, I should have been seeing many questions there. So, any questions? So, any questions? Like I said, question 9 and 10 will be in the discussion forum.